Hello. I promise I'm sitting or I'm between you and your lunch, but I'll make it quick. Hi everyone, I'm Joinal. I work at Microsoft as an AI architect specializing. Okay, I'm audible now? Yeah. Uh, hello again. I'm Joinal Ahmed. I work at Microsoft. Hello. Yeah. I work at Microsoft as an AI architect into Azure AI and OpenAI stack. Today, what I'll do is I'll talk around how do you scale these LLM inference. From last one and a half year, we've seen every product that we see wants to integrate LLMs into that, right? Or some form of machine learning that you want to integrate. So we'll talk around how these large models are deployed, integrated, and since everyone here knows about Kubernetes, I'll not go into how Kubernetes can help, but we can talk around how you can utilize it to scale these LLM inferences, right? And this is just in history, right? So this is how we have seen the rise of machine learning models right from 2018, where GPT was launched, the original GPT was launched, to today, or right? We have Llama, Mistral, GPT-4 Vision, and whatnot, right? And every product that you see has used some version of it. And I like to call this as LLMs as flavor of the season, or in Hindi, what you call as tadka lagate, right? So every product has a flavor of LLMs into it. But before that, right, if you are a business owner or if you are a data science leader, you want to integrate some form of machine learning into, or LLMs into your product, right? So I'll just quickly cover how do you choose a machine learning model, then talk around how do you deploy it in a scale, right? I think that covers the whole journey. So you start with asking fundamentals, right? Do you actually need machine learning models, right? Is LLMs are actually required, right? So start with that, because these LLMs are costly, and I'm thankful that talks before me, they kind of establish the fact that these running these LLMs are a costly affair, and how do you scale that up, right? Then once you decide, okay, I need to go and use an LLM, then you decide, okay, do I need to use a pre-trained model? Do I need to use or train something that I would, for niche of my business, right? Then finally you go ahead, if you decided which way to go, then you go ahead and decide or explore, evaluate these models across accuracy and other metrics, right? Then you finally go ahead, if you want to train a model, it's a very big financial investment. At the same time, if you want to maybe use something out of the shelves, there is subsequent cost also attached to that, right? Then you finally go ahead and decide, okay, do I have proper licensing? Let's say, for example, there are a lot of open source models available, but you cannot use it for a lot of use cases, right? So you have to decide on licensing where these models can be used or not. So once you decide all of this, let's assume you ask all of these questions to you, to your business, to your teams, and you decided, okay, I need an LLM, this is the LLM that I'm gonna go, right? Now, the problem with this is, when you talk about deploying these LLMs, right? These are compute-intensive resources, right? You cannot necessarily run a machine or a ML model in the same infra that you run your other software products in, right? These are power and compute-intensive processes, and they need a very large infra. At the same time, scaling is the issue, right? Now that these models are very big, scaling them is tough, right? And we all know that today in this world, getting that access to GPUs is scarce, right? You cannot go into any cloud and directly provision a GPU machine, because those H100s and V100s are not available out of the shelf, as same as if you can deploy any ARM or AMD CPU machine that you can get, right? Third is latency, right? Since these models are large, or ML models in general tend to have a very large latency, right, on when you run them. So how do you also make sure that you don't make the user wait to get these predictions, right? If you say an LLM, right, it's GPT 3.5 or 4, the latencies are around 20 seconds per call, right? But you don't want the user to wait for 20 seconds, which is where Clever UX came in. They did a streaming of the response. So first response time is 150 milliseconds. So you get the first response and start streaming it back instead of the user waiting for the whole thing, right? Then there are issues around memory requirements and the model sizes itself. Uh, these challenges, right, if you look at a tool to solve, I think, you know, and people who are trying to, let's say, cover it from the journey, right, in the, until last year, we were talking around what is MLOps, how can organizations adopt MLOps. Today, the narrative has changed to around how can we do LLM ops, right? And this is nothing but a subset or a very niche subset of DevOps, right? So still these ML engineers that we call today are a mixed breed of DevOps engineers and software engineers who specialize in deploying these machine learning at production, right? And to solve all of these, right, Kubernetes comes to rescue. I think I started Kubernetes because I needed to deploy these machines at scale, and it helped me a lot, right? So I'll not go into discussing what Kubernetes provide. You guys know more than me and what Kubernetes provides you, right? But if you tell these things to a data scientist, right, that you would have to use Kubernetes and deploy this model, this is something that you will get a reaction, right? This is how they feel, right? We as a data scientist, we are accustomed to using Jupyter notebooks, write our code, and call it a day. But when you ask the same guy, go ahead now, productionize this, deploy it, it's a hard job for them, right? So which is where today I'll talk around some of the tools which are available, which is tooling which are available in the Kubernetes ecosystem. How do you use it? And for someone who is into DevOps, who is looking into, go towards LLMs and MLOps, this would be something tools that you want to explore and, have these skills in your belt, right? First is Kaito, right? It's an abbreviation of Kubernetes AI Toolchain Operator. So what it does is, we all know these machine learning models, they love GPU, right? But at the same time, as someone who's provisioning them, it is very hard for me to guess which GPU is fit for my model. So Kaito does that job for you, right? You provide the model specifications. It kind of regresses to which specific instance you would use so that these workload can be taken care of, and it automatically spins that up, right? At the same time, models doesn't like to share GPUs, right? Traditionally, if you want to run one model, it just takes up the whole GPU, right? You could not fit two models on the same GPU. Kaito solves that for you, right? So you can necessarily now have multiple GPUs, let's say multiple models, one large model, couple of small models running on the same GPU, so you get the cost benefit of using that GPU. Sorry? Yeah.
What's that? Limits and, minimum and maximum, right?
Yeah.
For the normal compute, we can say that start with small and that min max we can define. Documentation, it's mentioned that.
Yes, right. It was until last year, the paradigm was that, right? So there have been recent advances. I'll talk around how this is implemented. But at the top level, you could now share GPUs across your deployments of ML models, right? So multiple models can use the same GPU without doing I/O switches, right? Without writing it on I/O and then loading it back, right? So you could do that today. Yeah, using Kaito. I think it's a project which was open source 2 months ago. It's a very new project, and I had deployed this in a couple of use cases. You can get up to 23x more performance. We'll see those benchmarks and how it performs, right? Essentially, this is how it works, right? So there is a workspace controller, which has all the CRDs, and you define your custom CRDs, right? And then on top of that, there's a node provisioner. So what workspace controller does, it reconciles the workspace definition that you have provided, right? It controls that, and when you do you create a YAML configuration of your model defining what the model needs, then it goes to that, the node provisioner triggers, you have your, traditionally you have those containers in a public registry or a private registry, right? It pulls them up, calculates how much compute is required for it, tries to see if the available compute that it has can cover it or not. If not, then it will spin up, or it will try to fit everything into the current infra that it already has, right? And the setup is very straightforward, right? You just don't need to do much. You just need to write that configuration. I think I have that YAML. But essentially, you just need to write that basically in this demo, you will log into your Azure account, define or take federate the identity and provide that identity to the node provisioner, right? Now it calculates it, provisions it for you. Second, and then this is where it gets interesting, right? So Kaito uses some of the goodness from VLLM to do that, right? So what VLLM does is, there are a lot of big words, right? High throughput, memory efficient. It uses something called as a paged attention. If you, from software engineering, we know KV caches and how they're used, right? So it uses KV caches to now store or retrieve those weights, the tokens that you input, and then scales it up, right? It uses something called as a continuous batching, and it is optimized for CUDA kernels, right? And it natively supports majority of all LLMs that we see today. If not, there had been work to support those LLMs also to deploy and scale. These large words might seem very complex, but it's not that, right? I'll tell you how things are, right? So just primer on how LLM works. So this is how yellow words are your input, right? Let's say write a agenda for KCD talk, right? So maybe these yellow words are like that, right? Then green word is the context that you extract. And then it predicts those words, right? And then the red is when it ends, right? So it gives you that last sequence. So if you see these white empty boxes, this is the space you are wasting, right? In that each compute, right? You're not utilizing those. And just basics, right? So it's auto-regressive. These LLMs don't predict the entire sentence in one way, right? Just predict next word. It'll take the whole thing as an input and predict next word, right? It does that. Instead, what you do is, and this is static batching, right? If you see the T7, T8, and those empty boxes, this is what you are wasting. This is the memory you are wasting in those GPU, right? In each iteration, each prediction. Instead, what you do is something called as a continuous batching, right? So you start right from where the last sequence ended, you use it, and then move to the next batch, right? So you continuously keep on using everything, all the available space to you, and then move to next, right? So that way what you do is now, and this is better at scale, because at scale you'll have more wastage, and you try to overcome or use those wasted memory using continuous batching. Yeah, I think that's all. And then there is something called as a paged attention, right? So what happens is it's same. When you load to input, right? What traditionally LLMs used to do is it used to find out continuous memory available to fit everything, versus what it now does is it tries to see wherever and whenever I can fit these things into memory. And then from there uses a KV cache to map it. Let's say, first chunk is in this part of the memory, next chunk is, maybe some random addresses. It all links it up using a KV cache, and then you can directly access them, right? And now what advantage it also gives you is now, since these are mapped using a hash table, you can access, different deployments can use the same KV cache, right? So you're not re-initializing everything for each inference multiple times. And it's a straightforward, Python library you can right away use. So what you do is initialize that LLM construct, load the model, and start generating, right? So all these goodness are automatically taken care of the library for you itself. Yeah, so this is the whole stack, right? At the core, there's Kubernetes. On top of that, you have VLLM, Typetron, DeepSpeed. There are a lot of accelerators which are available. And on top of that, you have your K-serve, which is Kubeflow serving construct. Then you have NVIDIA's Triton server, Hugging Face library, and all of that, right? Second is, I think something what I want to talk about is anatomy of how these models are deployed, right? So traditionally, if you see, red bar is what you input, and there is a base model, right? Let's say a large model which is in memory. And then if you tune or if you fine tune one model, then you basically add that small blue box, right, to that additional knowledge, and you now deploy this. At scale, what happens is if you're now getting a lot of requests, right, you would just duplicate this, right? That's how we know scaling is, right? So you'll just duplicate this and try to address that traffic, right? The problem with this is now for every scaling, you'll need a new GPU, right? You'll need a new GPU to fit that, right? And it seems something like this, right? You're just duplicating the same construct, you are just multiplying the whole infra that you're using, and your costs are now running out of boundaries, right? Instead, what you do is there's something called as LoRax, right? LoRa exchange, right? So what LoRax now does is, instead of you deploying everything, same model multiple times, you deploy your base model once, which is that yellow box, and you deploy these small weights parallelly, right? And what you do now is you inference the base model plus all of these together, and then use a mask at the end to see, okay, this is mask I want to use and others I don't want, so 1 and 0, right? So you multiply that by 0 and it goes, all of these gets nullified. Along with that, what it uses is something called as an tired caching, right? So let's say your models or weights which are getting a lot of high traffic, this will be always in memory. Then there is a secondary which is on, let's say, on the disk, right? And then it can quickly load it for models which are less frequently used. And the models which are rarely used, this will be stored or offloaded into some blob storage somewhere. And if there is an need, those will be loaded, right? So on top of the goodness is that LoRax tries to also predict when I can expect an inference for this model, right? It tries from the traffic load, it learns that, I might expect that weight to be, called at, let's say, X timestamp. So it tries to predict it and preloads it, right? So you also don't have then any load start time or cold start time for these models, and your inference increases. So instead of doing this, if you combine everything, you would do something like that, where you just deploy your base model once and you deploy all of the adapter weights parallelly and use them at the same time. And this is what it means in terms of latency, right? I think I just have 3 minutes, I'll be fast. So this gray line is what it means. It's a break-even threshold. So if you do the traditional way of scaling, that is what you'd achieve. Versus now, if you use LoRax and a couple of these things, you will see, there is a big delta that you achieve in terms of cost and throughput, right? But it also diminishes at scale, right? Let's say if you have more than 125 deployments, which is not a reality, right? You'll not have 125 LLMs running at a parallel. At the same time, if you just have one model, very low usage, if you now deploy with this, you'll not see much of an gain. But if you have somewhere around 20 to 50 models, which average good traffic across all of them used, so you'll see a lot of advantage there. To sum everything up, this is how it looks, right? So you have your LLM service where all your Llama model or these models are deployed. On top of that, there is an Kubernetes API server which manages all of them. So it now takes the traffic, decides which adapter to go, and these models are now uses Kaito and VLLM at the core to optimize it further for you. I think I'll be quick. Yeah, I wanted to show this, right? So if you see these numbers, right, and this is an benchmark across all or 4 major ways to deploy these models. And if you combine everything using continuous batching, VLLM, Kaito, you get upwards of 23x performance with the same hardware, with the same compute, right? So this is what I wanted to show you, the goodness that now can be achieved with these open source tools, which was not possible maybe a year ago. At the same time, if you see the latency, right, your throughput and latency is also optimized. Now you can get more throughput, more tokens generated for the same amount of compute at the same amount of time. And these are some resources. If you want to read, go ahead, read about them. Maybe reach out to me if you need any further help. And yes, I think that's all. That's all I had. And yes, if there are anyone going for KubeCon Europe, there will be a detailed workshop on this at KubeCon Europe. So if you're not attending, there would be recordings that you could access and see again. I think that's all. Thank you. You can reach out to me. You can scan this deck if you want to just get access to the deck and see it on yourself. And I also run a meetup community at Bangalore, where we talk about a lot of these practical things. And I tend to do it in person so that we can also learn from each other and do these things. I think that's all. Any questions? Anything? Happy to answer.